Hello. In today's lesson, we will continue our discussion on wave motion by talking about stationary waves. Now, let's begin with a review of what wave motion is. Anybody tell me what your understanding of wave motion is? Well, try and review it in your mind. Wave motion is the propagation of energy in a medium by setting the particles of the medium into vibration. And we've discussed the vibrations of the particle in detail in our lesson 1. Suppose this is one particle in vibration. Now, you know that this particle vibrates about the equilibrium position, goes up to the upper extreme, back to equilibrium, down to the lower extreme, back to the equilibrium position. That is one complete vibration. Now, what happens if this particle is now under the influence of two different waves? What does that mean? Suppose you put two pebbles onto a pool of water. It will create two disturbances, and every water molecule will be subjected to the energy coming from both these disturbances. That means each particle will have to obey instructions from one disturbance and also the other disturbance. For example, if this particle is going to be in the upper extreme due to one disturbance, and due to the other disturbance it has to be at the lower extreme, what will this particle do? This particle has been instructed by disturbance 1 to be at the upper extreme and disturbance 2 at the lower extreme. That means this particle will not vibrate. Is that right? So depending on how the two disturbances superimpose on each other, the state of vibration of a particle will change. Now, the two waves can be in phase. What does that mean? If this particle can be in the crest of one wave and the crest of the other wave, that means both the waves want this particle to move in the same direction. What will this particle do? It will vibrate with double the amplitude. On the other hand, if due to one wave it is supposed to be on the crest, and due to the other wave it is supposed to be on the trough, the particle will not vibrate. Alright, let me bring out those points a little more clearly. Let us look at the direction of vibration, the direction of displacement of the particles as a wave advances in a medium. Now, as a wave advances in a medium, the particle vibrations describe crests, trough, and so on. Now, suppose a particle is on the crest. What is the state of vibration of that particle? Anybody tell me what is the state of vibration of a particle on the crest? It has gone all the way to the top and it is now ready to come down. That's right. That is the state of vibration of that particle. Now, how about a particle in a trough? What is the state of vibration of such a particle? It has actually reached the lower extreme. It is now beginning to go up. That means the state of these two particles are completely opposite. Or we say they are completely out of phase. Is that right? Okay. Now, what will be the state of vibration of a particle that is on the crest of one wave and the trough of a second wave? We talked about that. Now, suppose there are two waves and a single particle is on the crest of one wave at the same time the trough of the other wave. That means due to one wave it wants to move down and the second wave wants it to move up. What will the particle do? Well, a particle here, it is on the crest of the first wave. That means it is beginning to move down there. And the trough of the second wave, it has to move up. That means that particle will not move. The particle will have no displacement. Now, as a result, what happens is a wave can meet with another wave at a particular point, producing no wave or complete destruction. It can also produce a bigger wave. Is that right? Okay. Now, if the particle is on the crest of both waves, the displacements will add up, and the superposition then is said to be constructional, or it is a constructive superposition. So, waves meeting at one point, two different waves meeting at one point, can either be constructive or can be destructive. Once you understand this, then understanding of the waves will be very simple. Now here I have one wave, the red wave, another wave, the green wave, are in phase. What does that mean? It means the crest of one wave falls on the crest of the other wave. So a particle of the medium there will be subjected to displacements in the same direction by both the waves, and therefore the particle will have double the displacement, or we generate a much bigger wave. You see, a wave meeting another wave produces a much bigger wave when they meet in phase. Okay, so the waves meeting at a point can interfere constructively like this, or destructively like we saw in the previous slide, producing either a bigger wave or sometimes no wave at all. Okay, now we can demonstrate that using this apparatus. Now let me see if I can demonstrate that to you. Give me a second to set it up. Alright, I want you to watch the way this string vibrates. Now look at the shadow on the screen rather than on the string itself. Now what happens is, this is a mechanical vibrator which vibrates up and down with a particular frequency, sending a wave down the string. Now when the wave reaches the other end, it reflects backward. Now let me turn this off and talk about that. Alright, what I'm doing is, if I produce a disturbance on the string, that disturbance travels down the string and it gets reflected. That means each segment on the string is subjected to the wave that is advancing and the wave that is reflected. Now, depending on whether these two are in phase or out of phase, each segment on the string can either have a maximum displacement or minimum displacement. Okay, let me set that again there for you. Now, I've got to adjust the frequency in order that this may happen. So, watch that carefully. Let me adjust the frequency, see if I can get that right. Now, this mode of vibration of the string, what you see here is that the segments at the middle have maximum displacement. So the advancing wave, you can see the advancing wave and the reflected wave are actually meeting in phase there. And at the two ends there are no displacements at all. Is that right? Now look at the next mode of vibration. The frequency of vibration of the string now is about 10 Hertz. Now, if I increase the frequency to about 20 Hertz, there I have about 20. Now, what you notice here is that the string vibrates in two segments. Now, we will look at this a little later, but let me put this away now for the time being. Okay? So, what I have created here is stationary waves on a stretched string. As the mechanical vibrator moves up and down, an advancing wave and a reflected wave meet, and depending whether they meet in phase or out of phase, the segments of the string can have maximum or minimum displacements. Alright, so you have two waves. Each particle on the string is subjected to displacements due to the advancing wave and the reflected wave. Okay, there is the advancing wave, and I represent that by the green wave. Alright, and now this is the reflected wave, the red wave. So every particle on the string is subjected to the advancing wave and the reflected wave. Now tell me, what will be the state of vibration of the string when the two waves are meeting like this? Are they meeting in phase or out of phase? When they are like this, the crest of the green wave and the crest of the red wave are together. Similarly, the troughs are together. They are in phase. That means each segment of the string at that time will have maximum displacement. But remember, this is only momentary. The green wave is advancing to the right and the red wave is advancing to the left. Can you construct a mental picture? What happens a little while later? The green wave is moving forward and the red wave is moving backward. You can imagine a particle somewhere here will soon be on the crest of one wave and the trough of the other wave. So the instant when the crest and the trough of both waves coincide, the string segments have maximum displacement. So the string will vibrate with maximum displacement. That's what you actually saw. Alright, this happens only for an instant. Why is this only for an instant? Because the green wave is moving to the right and the red wave is moving to the left. So this situation will not last. Okay, soon the crest of the advancing wave falls on the trough of the reflected wave. There we are. Because the green wave has advanced to the right and the red wave has advanced to the left, this situation comes in a little while later. You see that? So what is happening to these segments of the string now? Now, at that instant, all the segments now are subjected to opposite displacement and they all remain stationary. Now, this again is momentary. Why? Because the green wave is advancing to the right and the red wave is advancing to the left. Now, that means a little while later, the crest of one will fall on the trough of the other. So, what happens? As these two waves, the advancing wave and the reflected wave, continue to advance in the opposite directions, the string segment simply will have maximum displacement, no displacement, maximum displacement, and so on. So you will simply see the segments of the string having maximum displacement, minimum displacement, and this process will continue. And that is what is called stationary waves. Why do we call them stationary waves? Well, because the string segments simply vibrate with maximum and minimum displacement. And that is not advancing. What is advancing are the advancing wave and the reflected wave. But the stationary waves simply have maximum and minimum displacements appearing and disappearing at equal intervals of time. Alright, so this process repeats in time, producing the states of maximum and minimum displacements alternatively. And because it happens very fast, we very often see only the maximum displacements. Alright, so this is what you actually see. But what actually happens is the string segments will have maximum displacements, minimum displacements, maximum displacements, and so on. Now, there are some points on the string that will be permanently at rest. And those points are called nodal points. Now, how many nodal points are there? This is a node, this is a node, this is a node. And we will represent it by n. So let's mark all the nodal points. That is a node, that is a node. Now, points which have maximum displacements are called antinodes. How many antinodes are there? This is an antinode, this is an antinode. So again, points where the string segments are permanently at rest are called nodal points. And points where the string segments will have maximum displacements are called antinodes. So a stationary wave is actually characterized by the formation of nodes and antinodes. So this process of maximum and minimum displacements appearing and disappearing is called the formation of stationary waves. Okay, the wavelength lambda of a stationary wave. Now, anybody know how we define wavelength? That's something that you cannot forget. What's the definition of a wavelength? Well, I gave you different definitions. A wavelength is the distance advanced by the wave by the time a particle completes one vibration. In other words, the distance advanced by the wave in one period. And you know that this is one complete wave. Is that right? A wave has a crest and a trough. So one full wave contains a crest and a trough. Therefore, the distance between two alternate nodes, you notice that? Not the nearest node. The distance between two alternate nodes is a wavelength for a stationary wave. The wavelength lambda of the stationary wave is the distance between two alternate nodes. There you are. So don't forget that. There's an easy way to remember that. Because when you see stationary waves, do you notice that there are loops formed? L-O-O-P, loops. Is that right? Now, if you measure the length of two loops, that will be a wavelength. Is that right? Now, you want to take a look at that demonstration one more time? All right. Now, here I have that demonstration one more time. And here, the string is actually vibrating in two loops. And so, if you want to measure the wavelength of this wave, what all you need to do is to measure the length of these two loops. There you are. Now, look at the way how clearly the nodes and antinodes are defined there. Look at the node there. A particle here or a segment there never has any displacement. That's a node, this is a node, and that is a node. Here's an antinode. A particle will have maximum displacement, and here again is an antinode. If you notice that what actually the string does is the segments of the string are having maximum and minimum displacement alternatively. How many times? The frequency here is 22 Hertz. Now it's doing 22 times a second, and that's why we see it just the maximum only. Okay, let's push that away for the time being, and I will bring it back again for another demonstration. Okay. Wavelength is the length of two full loops. Now that's a useful information to remember. The wavelength is the length of 2 full loops. The number of nodes and antinodes on the string depends on the frequency of vibration of the string. Now if you noticed, when the frequency of vibration here was 10 Hertz, we just had 1 loop. And the frequencies increased to about 20 Hertz, there are 2 loops. And so on. We will talk about that again as we move on. Now let me see if I can access this website and show you this process a little more clearly. Give me a second if I can access it. Now here, there is an advancing wave and that's getting reflected. Watch that. Oh, how beautiful. It's getting reflected and each segment on the string is now subjected to the advancing wave and the reflected wave. What is happening? Each segment is having maximum and minimum. Watch it again. It gets reflected. The reflected wave and the advancing wave are now superimposed on each other. And you can see points where the segments are permanently at rest. They are nodes. One more time. The advancing wave, the reflected wave, they are interfering, producing maximum, minimum displacements. You have nodes, antinodes formed continuously. Now, let's look at the fundamental mode of vibration. Now, this is the fundamental mode of vibration. The string vibrates in just 1 loop. You see that? And if you look at the bottom one, you got the second mode of vibration. The string vibrates in 2 loops. The frequency of this vibration is twice the frequency of the fundamental. We will take it up again. And you can have the next higher mode. The string vibrates in 3 loops. And so on. Alright, let's turn that off. Now, the simplest mode of vibration, we call the fundamental mode of vibration, is that it has nodes at the fixed end and antinode at the middle, and it looks like this. If I make a drawing, you got a node and a node there and an antinode at the center. This is called the fundamental mode of vibration. And the frequency of vibration of the string when it vibrates like this is called the fundamental frequency. You see, when you strike a guitar wire, most often it vibrates like this, and the sound you hear is the sound of its fundamental frequency. Now, for the fundamental mode, the length of the string contains, let me ask you, you now know what wavelength of a stationary wave is. Now, how many loops are there in one full wave? There are 2 loops. Therefore, what is the wavelength of this fundamental mode of vibration? You see, the fundamental mode contains only 1 loop. So 1 loop is half a wavelength. Is that right? So, for the fundamental mode, the length of the string contains half a wavelength. So I can say L equal to lambda by 2. And therefore, what is lambda equal to? Wavelength of this fundamental mode of vibration, therefore, is 2 times the length of the string. Lambda equal to 2L. Okay, what is therefore the frequency of vibration? Anybody tell me how we can write an equation for frequency? If you know our fundamental wave equation. V equal to F lambda. Have you forgotten that? If V equal to F lambda, what is F equal to? The frequency of the fundamental mode is F equal to V over lambda. Is that right? And I'm going to denote the fundamental frequency as F1. And in place of lambda, I'm going to write 2L. So, the fundamental frequency of vibration is F1 equal to V over 2L. I'm going to leave it there for you. F1 equal to V over 2L. Alright, let's now look at the frequencies of higher modes of vibration. In the next higher mode, the string vibrates with 3 nodes. A node here, a node there, and a node there. There are 3 nodes and how many antinodes? Antinode, antinode. Now, who can tell me what is the relation between the length of the string and the wavelength now? How many waves are contained in the length of the string now? Well, if you understand that concept, you know that the string now contains 2 full loops. That is the whole wavelength. Is that right? Yes. And the frequency of this mode is called the second harmonic of the string. When a string vibrates like this, the frequency of vibration is called the second harmonic. So the basic mode is the fundamental. The next mode, the frequency is the second harmonic. And for the second harmonic, the length of the string contains 1 full wavelength. Therefore, we can write lambda equal to L. Alright, what is the frequency of this mode of vibration? The frequency is F2. I'm going to call the frequency of the second harmonic F2. V over lambda, is that right? Frequency is always V over lambda. But lambda this time is equal to L. So let's replace that. Okay. Now I'm going to rewrite this. Look at the way I'm going to rewrite it. V over L is written as 2 times V over 2L. Is that right? Why did I do that? Because V over 2L is the fundamental frequency. You remember that one? So, the frequency of the second harmonic is 2 times the fundamental frequency. When the string vibrates in its second harmonic, the frequency of vibration is twice the fundamental. Now, how about the next higher mode of vibration? String vibrates in how many loops? 3 loops. There is a node there, another node, another node, another node, and antinode, antinode, antinode. Alright, who can tell me now what is the relation between the length of the string and the wavelength? How many wavelengths are contained in the length of the string? You can see wavelength is the length of 2 loops. So this is 1 full wavelength. And you have another half a wavelength. So the length of the string now contains 1.5 wavelengths. There you are. And the frequency of this mode is the 3rd harmonic of the string. Alright? We can therefore write wavelength is 2/3 of the length. Is that right? This is the wavelength. Now this wavelength is 2/3 of the whole length of the string. So the lambda for this mode is 2/3 of L. How would you now write the frequency in this case? So the frequency of this mode F3, again, frequency is V over lambda. But what is our lambda? Lambda is 2/3 of L. Let's replace that. So that will be V over 2/3 of L. Okay, can you write this in terms of the fundamental frequency? Look at the way I'm going to write it. That will be 3 times V over 2L. Is that right? This 3 goes up. And what you have here is V over 2L. 3 times V over 2L. And what is V over 2L? V over 2L is the frequency of the fundamental. So that will be 3 times the fundamental. That's not very difficult. Alright, now I have put all these down together for you. The fundamental is the first harmonic. And what is the frequency of the fundamental? The frequency of the fundamental is V over 2L. What is the frequency of the second harmonic? The frequency of the second harmonic is 2 times the fundamental. You see, V over 2L is the frequency of the fundamental. 2 times the fundamental. What is the frequency of the third harmonic? 3 times the fundamental. What is the frequency of the fourth harmonic? 4 times the fundamental. What is the frequency of the fifth harmonic? 5 times the fundamental. Alright. Let's now use this quickly to explain the meaning of quality or timbre of a musical note. Now, how many of you are familiar with music and musical note? Well, when you strike a guitar wire, you hear a beautiful musical note. A musical note is a pure frequency. And what you hear is mostly the fundamental frequency. But very often, the string, when it vibrates, in addition to vibrating in its fundamental frequency, it also vibrates in the higher harmonics. That means, very often, the higher harmonics are superimposed on the fundamental. Well, about 95% of the sound you hear is actually the fundamental frequency. But that fundamental frequency can be modified by superimposing the higher harmonics. Now, if you strike a guitar wire and a piano wire of the same frequency, they don't sound the same to you. Although they have the same frequency, they sometimes sound differently. You see, you can distinguish a note played on a piano and a note played on a guitar, although they are the same. Now, what is that particular characteristics which lets you distinguish between a note that comes from a piano and a note that comes from a guitar, or the same note that is produced on a drum? The difference is, although the fundamental frequencies are the same, the combinations of higher harmonics are different. And these combinations of higher harmonics are actually determined by many physical characteristics, such as the material with which the musical instrument is built. All those will go into making the quality or timbre of the music. Alright? So I want you to have a clear understanding of the meaning of timbre of a musical note. When a stretched wire of a piano is struck, it vibrates with notes at the fixed ends and antinodes at the center, emitting its fundamental frequency. There you are. Okay. Along with the string vibrating in its fundamental mode, it can also vibrate in the higher harmonics. That means the sound you hear is actually the superposition of the higher harmonics with the fundamental, although most of what you hear is the fundamental. It is this combination of the higher harmonics with the fundamental that gives a musical note its unique quality, that distinguishes a note from a guitar, that from a piano. You see, that's what distinguishes every musical instrument. Every musical instrument produces its own quality or timbre musical notes, because the superposition of the higher harmonics is different in different instruments. Okay, let's now talk about the laws of transverse vibrations of a string. What are the laws governing the transverse vibrations of a string? Now, before we go on, let's take a look at our demonstration one more time, just to make sure that we have these various modes understood. All right? Now tell me, what is the mode of vibration now? The string is actually vibrating in 2 loops. So this is the second harmonic. Let's go and have a look at the first harmonic. There you are. That is the first harmonic. You got the string vibrating in 1 loop. And now, if I change the frequency, you can see that disappears. It only happens at a particular frequency. And now I'm going to increase the frequency. It is now 14. It's coming close to 20, and you can see it's now vibrating in 2 loops. The second harmonic. The frequency of the second harmonic here is 20 Hertz. The fundamental frequency was 10 Hertz. Alright, I'm going to increase the frequency. You can see that disappeared. That means the superposition now is not in a position to create maximum and minimum displacements at this frequency. Alright, let me increase that frequency again. Alright, it's coming close to about 30. And now, this is the third harmonic. You can see how clearly you can see the string vibrating in 3 loops, the third harmonic. Now the frequency is 30 Hertz. Alright, let's go and do the fourth one quickly. There you got the fourth harmonic. Okay. It'll be fun to work with this. You will be doing a lab on this. Alright, let's look at the fifth harmonic. Did I get the fifth harmonic? There you are. That's the fifth harmonic. The frequency is 50 Hertz. Let's do one more. Can I get 6? There you are. That's the sixth harmonic. Well, let's now look at the laws of transverse vibrations of a string. When you talk about the laws of transverse vibrations of a string, we're going to concentrate on the fundamental frequency. The fundamental frequency. Now, does anybody remember the equation for the fundamental frequency? What is the frequency of the fundamental of this? I'm going to put that away. Anybody remember? Well, the frequency of the fundamental. Now, let's start with this. What is the speed of transverse waves on a stretched string? You remember this equation. V equal to square root of T over mu, where T is the tension on the stretched string, and what is mu? The mass per unit length. Alright, so T is the tension and mu is the mass per unit length. But V, if you remember your wave equation, V equal to F lambda. So let's use that over there. We have F lambda equal to square root of T over mu. Can you solve for frequency from here? What is the frequency of vibration of a stretched string? Well, F equal to 1 over lambda square root of T over mu. Now, this is the general equation for the frequency of any stretched string. Now, this can now be used to obtain the frequency of the fundamental. What all you need to do is replace lambda by what? What do we replace lambda when you want to find the frequency of the fundamental? Because the fundamental lambda equal to 2L. When you want to find the frequency of the second harmonic, replace your lambda by L. When you want to find the frequency of the third harmonic, tell me what you replace your lambda by? 2/3 L. That's right. So this is the equation, the general equation of the frequency of vibration of a stretched string. When a string vibrates in its fundamental, then lambda equal to 2L, And so that's the fundamental mode of vibration. The wavelength is twice the length of the string. And therefore, we can write the equation for the fundamental. This equation is the equation for the frequency of the fundamental. I replaced the wavelength by 2L. And we are now going to use this equation to describe the laws of transverse vibrations of a string. Actually very simple, because if you look at this, what are the factors on which the frequency depends? Frequency depends on length. Now, how is the dependence? Is it direct variation or inverse variation? Frequency varies inversely as length. It means shorter the length, higher is the frequency. If you look into a piano, you will see the very high frequency notes are produced by very small length of wire, whereas the low frequencies are produced by long wires. Those who play guitar will know that, how you change the position of your finger to produce low notes and high notes. Okay, and the frequency is directly proportional to the square root of the tension. The guitar needs to be tuned very often, because you keep plucking it, its tension will change. When the tension changes, its frequency will change. Is that right? Okay. Also, the frequency depends on the mass per unit length. Let's write all down in our next slide. The first law, the fundamental frequency of a stretched string is inversely proportional to its length when T and mu are kept constant. That's the first law. Second law, the fundamental frequency of a stretched string is directly proportional to the square root of its tension when the length and mass per unit length are constant. And the third law, the fundamental frequency of a stretched string is inversely proportional to the square root of mu. That means a thicker wire, tell me, a thicker wire, will it produce a high frequency or a low frequency? A wire is thick means mass per unit length is greater. When mu is greater, the frequency will be low. So a thick wire will produce a low frequency. If you look on the guitar, there are different thickness of the wires. They are meant to produce varying frequencies. Alright. The fundamental frequency of a stretched string, I told you this before, in order to change this to the fundamental, what all we need to do is replace lambda by 2L. So frequency of the fundamental is this. Okay. How about the frequency of the second harmonic? The second harmonic, you replace lambda by L. And that will be 2 times the fundamental. And when the string vibrates in its third harmonic, the frequency will be given by replacing that lambda by 2/3 of L. There you are. And that will be 3 times the fundamental. We saw that several times in this lesson. Similarly, the frequency of the fourth harmonic is 4 times, and so on. The higher harmonics are also called overtones. Now, the fundamental is also called the first harmonic, but the first overtone is actually the second harmonic. So look at that. Higher harmonics are called overtones. The first overtone is the second harmonic. The second overtone is the third harmonic, and so on. All right. Let's spend some time now solving some problems. A string fixed at both ends is 3 meters long. All right, anybody tell me, what is the wavelength of its fundamental mode of vibration? if the string is 3 meters long, what is the wavelength of the fundamental mode of vibration? Well, if you recall, the wavelength of the fundamental is 2 times the length. Okay, it resonates in its second harmonic. So the string is vibrating in its second harmonic. Alright, what is the wavelength of that wave? The wavelength for the second harmonic is the same as the length of the string. Alright, and the frequency of the second harmonic is 60 Hertz. Alright, if the frequency of the second harmonic is 60 Hertz, what is the fundamental? I'm simply asking you this to take you back into to see whether you are in sync with what I'm talking about. Well, if the frequency of the second harmonic is 60 Hertz, the fundamental is 30 Hertz. What is the speed of transverse waves on a string? What are the information you need to find the speed of a wave? Well, let's pick the data here. Length of the string is 3 meters. The frequency of vibration, the second harmonic, is 60 Hertz. Now, a string vibrating in its second harmonic vibrates in 2 loops. That means it is vibrating like this. Or the full length contains 1 wavelength, lambda equal to L. So the wavelength is the same as L, which is 3 meters. Well, we know the wavelength, you know the frequency. Can you calculate the wave speed? What equation will you use? Well, wave speed is V equal to F lambda, and you got both the values, and that wave speed is 180 meters per second. You can see, once you know the fundamental ideas, problem solving is very simple. Okay, let's do another one. A steel wire having mass per unit, having a mass of 5 grams and a length of 1.4 meter. I've given you the length of the string, I give you the mass. What can you calculate from those two? You can calculate the mass per unit length, mu, is that right? Very well. It's fixed at both ends and has a tension of 968 Newton. See, when you read a problem, you need to construct a mental picture. See, the information I gave you, the mass and the length will help you find mu, the mass per unit length. Then I give you the tension. What can these two information be used for? We can use it to find the speed of the wave on the string. What's the equation for the speed? V equal to square root of T over mu. So find the speed of transverse waves on the wire. We have done that already, is that right? Alright, find the wavelength and frequency of the fundamental. Well, if you know the length, then you know the wavelength of the fundamental. Once you know the wavelength and the wave speed, we can calculate the frequency. Is that right? Find the frequencies of the second and third harmonic. If I can now leave it to you, I'm sure you can do them on your own. Mass of the string, always remember to use the proper unit. 5 grams is 0.005 kilograms. The length of the string is 1.4 meter. The tension is 968 Newton. So first we calculate mu, the mass per unit length. Mass divided by the length. And that's equal to 0.0036 kilogram per meter. Alright, we now know mu, we know the tension. Let's now calculate velocity or the speed of this wave. Speed equal to square root of T over mu. T we know, mu we know, so use those values there. And that gives you 519 meters per second. Okay, so we did the first part. How about the second part? Find the wavelength and frequency of the fundamental. Well, the fundamental, if the length of the string is 1.4 meter, what is the wavelength of the fundamental? The wavelength of the fundamental is twice the length of the string. So that will be 2.8 meter. And once you know the wavelength and the wave speed, you can calculate the frequency. Let's do that here. Wave speed is 519 meters per second. And wavelength of the fundamental is 2L. There you are. And that's equal to 2.8 meter. The frequency of the fundamental is V over lambda. Well, the frequency of any vibration is V over lambda. But it becomes the fundamental when lambda equal to 2L. So in this case, it will be 519 meters per second, and lambda equal to 2L is 2.8 meter, and therefore the fundamental frequency is 185.35 Hertz. Alright, now tell me, find the frequencies of the second and third harmonics. What is the frequency of the second harmonic? Well, the second harmonic is twice the fundamental, that is 370.7 Hertz. And the third harmonic is 3 times the fundamental, that is 556 Hertz. Okay, let's do another problem. The length of the B string on a certain guitar, the B string, that's the note, is that right? The various notes, how many of you know the notes? You see, if you know the notes, do, re, mi, fa, sol, la, ti, is that right? Yes, each note. So B is the note, A, B, C are different notes, and the guitar has strings for various notes. The length of the B string on a certain guitar is 60 centimeter, and its fundamental frequency is 247 Hertz. You see, look at the information. You can actually obtain many other information using that. You are given the length of the string. You are given the fundamental frequency. What is the speed of transverse waves on the string? Well, speed V equal to F lambda. You know F. You know lambda from the length of the wire. Therefore, you can calculate the speed. Let's take the data now. Length of the string is 0.6 meter. The fundamental frequency is 247 Hertz. Mass per unit length. Are we given there? It is given for B part. 0.01 gram per centimeter, which is the same as 0.001 kilogram per meter. I hope you understand how to convert that. Alright, let me know if you need help there. The wavelength of the fundamental is lambda 1 equal to 2L. The wavelength of the fundamental is twice the length of the wire, and that is 1.2 meter. And V, the wave speed, is F1 lambda 1. The frequency of the fundamental is 247 Hertz. Lambda is 1.2 meter. Therefore, the wave speed is 296.4 meter per second. What's the B part? If the linear mass density is this, what should be the tension when it is in tune? What does it mean when the string is in tune? If the guitar is not in tune, have you seen anybody tuning a guitar by turning the knob, by adjusting the tension? Well, but the string is in tune means its frequency is truly 247 Hertz. Well, we need to find the mass, we need to find the tension. Well, can you form a strategy for that? How do we find the tension of the string? Well, obviously, you need to look at the equation V equal to square root of T over mu. Well, if you know your V, I think we just calculated the V, is that right? And you are given the value of mu, and therefore you can calculate T. Alright, so V equal to square root of T over mu. Solve for T, can you? Well, first of all, square that equation. V squared equal to T over mu. Therefore, T will be V squared multiplied by mu. There you are. T equal to V squared multiplied by mu. We know the value of V. We calculated that in the previous slide. We calculated the velocity to be 296.4 meter per second. So that will be mu times V squared, and that is 87.9 Newton is the tension on that string. I hope you can now solve problems of this type without any trouble. When you read a problem, always form a mental picture and pick out the data and see how best you can use them to find what is required. Alright, well, we have done a number of problems and discussed the concept of stationary waves. I will see you for the next lesson later on.